area. It's so lush. We got ferns and trees, and it just kind of sets the tone for what we're talking about is the movement of water through the environment. And so this course is mostly a surface hydrology course. There's also subsurface hydrology. It's a whole different discipline. We'll spend one class at the end of the semester learning some very basic equations in subsurface hydrology having to do with wells and water of movement, the movement of water under the soil. But if you were going to distill like why you're learning this information, what it's all about, into a single question, what do you suppose it would be? If you have a piece of scratch paper there, or maybe in the margins of your syllabus, write down, what do you think is the big question of this course? You know, like, there could be a course out there where the big question is, how much does a force deflect the material? Or there could be a course where the big question is, how does time affect the value of money? So, you know, that's an illustration of the big question of engineering cost analysis and economy. But what do you think, in a course about surface hydrology, what's the big question? Give you just another minute to think about it. All right, anybody interested to share what they wrote down as the big question for the course? What did you say, Jeffrey?
Why does the water act this way?
Okay, good. Why does the water act this way? That's an excellent stab at it. Anybody else go a different direction? Yes?
How much water is present on the surface of an area and how does it affect its surroundings?
Good. So the amount of water and what's the effect that that water has. Excellent. Well done. All right. So here's how I put it. For an area of interest, so we're talking about a certain area, what are the runoff characteristics? Now, to explain why I put it that way, what I have to do is draw the distinction between hydrology, oh, that marker's done, hydrology and hydraulics. Okay, now hydraulics, which some of you have done, some of you are doing later this afternoon, hydraulics is basically saying for a certain flow rate, how big of a pipe is needed. So that's the diameter of the pipe. You know, if we're talking about water that is moving through the environment, so open channel flow. For a certain flow rate, how big does the pipe need to be? That's what hydraulics answers. So what hydrology answers, what I said in words here, for an area of interest, what are the runoff characteristics? And so what we're doing is we're getting Q based on area, surface characteristics, rainfall, evaporation. So there's a whole lot of things that determine when it rains, how much water is actually getting to a certain place. So have you ever driven down Fifth Avenue on a rainy day? What did you notice as you drove down Fifth Avenue on a rainy day?
On the side, near the sidewalk, it pools up a whole lot of water.
It does. Yeah, it pools a lot. And if it's an extremely rainy day, is that like 4 lanes? Like the outer 2 lanes are no good, and you can only drive in the center 2 lanes, and so it really slows down traffic. So hydrology gives the hydraulic engineer the information that the hydraulic engineer needs to size the pipe. The hydraulic engineer just takes the defined flow rate and figures out how big the pipe needs to be. So what the hydrologist does is the hydrologist looks at how much is it going to rain, what is the area like is the water going to get down into the soil versus is it going to run over the surface? And so the hydrologist tells the hydraulic engineer how much water to expect. So here are all the inputs to that. We have to understand the characteristics of rainfall, not only how much rainfall there's going to be, like I'm sure you've heard, on the news, they'll say, well, it rained 0.7 inches today. Well, the amount is important, but the timing of the rainfall is just as important, maybe even more important than the absolute amount. In other words, when it comes. That's called temporal distribution. Is it going to be a very intense rainstorm all at once, like a thunderstorm? Or is it going to be like a long, low-intensity, drawn-out storm that maybe doesn't cause as much runoff at a peak time? Spatial distribution is talking about how is the rainfall variable over space. It may rain a lot at the airport, but does that mean it's going to rain the same amount in Huntington when we're X miles apart? Or are there certain features in the environment where it consistently rains more than others? So we'll look at all of these when we discuss rainfall. The hydrologist has to characterize infiltration. And so the hydrologist needs to understand the characteristics of the soil and also what's on top of the soil. You may have a really well-drained gravel and sandy soil, but if there is pavement on top of it, then there's not going to be very much infiltration. Or you may have a really nice grassy field that's not too steep, and you'd think, wow, grass can infiltrate water really well. But if there's clay soil underneath it, like at my yard, my house is like all clay everywhere. It does not absorb rain, and it becomes very squishy. And so that's one of the things that the hydrologist has to understand is the soil characteristics and land use. And also, this word antecedent moisture just means, is the water already saturating the soil from a previous storm? And so you have to make assumptions or have data that describes prior to your design event, the thing that you're planning for. You have to decide how often is your system going to fail. It's always going to fail eventually. The question is, do you want your system to fail once every 100 years, once every 50 years, every single year? You have different standards for different type of roads, for example. And part of that goes into the assumptions is how rainy it was before your design event. There are these things that are called abstractions, and what the abstractions do is they either reduce or delay the amount of water that runs off. So things like puddles or ponds, evaporation, interception by buildings, the wetting of a surface. Before the water starts to flow, the asphalt has to get wet. And so there are these things that we have to make assumptions about and study so that we know a little bit more about the timing of when the peak is going to arrive. You've maybe noticed before that when the rain starts, it's still dry underneath the tree, right? And it stays dry under the tree for kind of a long time, all things considered. You'd expect maybe that the water would just immediately run off the leaf, but the abstraction of vegetative interception can have a huge effect. And so we study those sorts of things. And there have been empirical evaluations done of different types of vegetation and how much of an abstraction they have. Now, this is all theory, and this next column is mostly practice-oriented. And so we have to understand like the fundamental forces of how water's moving around and really what's happening. But it's all so complicated that there's no fundamental way that we could say, an individual molecule of rain that's falling through the sky, where that molecule is going to end up. So we just have to use shortcuts to do that. And so we have to come up with approaches that describe the relationship between a certain amount and timing of rainfall with a certain amount and timing of runoff. And there is a graph called a hydrograph that is time versus flow rate, Q. And what we're often interested in, across the top of this, then we would maybe represent rainfall amount. And so, like, this scale is rain. And so it was a little bit of rain, and then it was a lot of rain, and then it was even less rain. So this is called a hydrograph. The rainfall part, and this runoff part is the hydrograph. And it's really important to know how long of a delay between when it rains and when the peak arrives. And so there's all these different methods that have been developed over the years in different places to try and understand what's the relationship and the delay between when it started raining and when the creek rises. It's not instantaneous, but the steeper the watershed, the more quickly that peak wave arrives. The more rocky and previously saturated the soil is, the more quickly that wave will arrive. And the shorter the time between the rain and the runoff also increases the amount. And so there's a relationship between the delay and the quantity. And so there's a lot of different techniques that have been developed over the years that allow us to understand this relationship between how much and when of the rainfall versus the runoff. Any questions so far as we're just taking this top level view of the concepts? I'd encourage you to occasionally, by the way, look back over this list that we're developing, because we're going to be getting deep into the weeds on things that just seem so obscure, like why does water evaporate? You'll be wondering, why are we talking about evaporation of water for a whole class period? And it's because we want to know about the abstractions and the things that reduce the amount of water that's getting to the runoff. So this is kind of like the time that we're going to look at it all at once in perspective. Routing is the idea that there's a delay once the water gets to the creek. Now the water is traveling down the creek. And so there's a travel time of just the water flowing through the river. And as the water is flowing through the river, the water at the bottom of the creek is moving slowly, and the water at the top of the creek is moving fast. Does everybody remember the idea of a velocity profile? You remember what we said is like, let's see. Okay, so this is depth, and this is velocity. So the shallow depth water isn't moving very fast, but the further away you get from the bottom of the creek, the faster it's moving. Everybody remembers the no-slip condition from fluid mechanics and the idea of a velocity profile. So as the water, this big surge of water, like if you think of it like a bucket of water got poured into the creek. Well, if you can pour that entire bucket of water into the creek all at once, a mile down the creek, it's not going to arrive in the same amount of time it took you to pour it out of the bucket. If you poured it out of the bucket in 5 seconds, it's not like a mile downstream suddenly a big surge of water just arrives and it all arrives within that same 5-second window. It's spreading out because the stuff at the bottom is moving slowly, the stuff at the top is moving quickly, and so that effect is the routing effect. It's travel time and delay. And so routing can be used to talk about hydraulic routing, which is the flow through the channel once it's already concentrated. But routing can also include analysis of shallow water flowing as a sheet over the surface of the land. And so it's aspects of delay time that are really important in saying to the hydraulic engineer, remember the hydraulic engineer, she wants to know what is Q to size the pipe. And so we have to account for all of the factors that are going to cause that flow rate. Finally, the implications of all this we're going to study this semester is pipe sizing and then also flooding. Communities that are adjacent to creeks. And if you think about West Virginia, like what community is not adjacent to some sort of a creek or a river? I honestly can't think of one. I mean, and the reason why is that that's really oftentimes the only flat land is next to the creek. And so people are in the habit of, well, I don't have to do the earthwork here because it's already flat, so I'm going to just park my house next to this creek. And then you're in a lot of risk. You're at risk of flooding. And so towards the end of the semester, we're going to combine hydrology and engineering economics and look at certain things we can do to reduce the risk of flooding and compare the value of those measures to the cost of those measures. And so we'll do a little bit of statistics, economics, combined with the hydrology, with risk assessment and floodplain management. So this is what we're doing this semester. Any questions? All right. Well, that leaves us, hold on a minute. Yeah, okay. So here's today's announcement slide. The Flume, Culverts, and HY8 assignment is due Wednesday of next week. It's available now for you to look at on Blackboard. You need to download and install the HY8 software and bring it to class. Bring your laptop to class on Wednesday. On Wednesday, I'm going to be demonstrating how to use HY8. And then on Friday, you're going to be using it to solve a couple of example problems. You may get a chance to actually use it also on Wednesday, but at the very least, I'd like you to have it installed so that you can follow along with the problem that I'm solving. Yes, Jeffrey?
So on the schedule here, so
Yeah.
if there's like a mark after a lecture, does that mean we're continuing on from the previous lecture today?
That's right. Yeah.
Okay.
Yeah, so Friday, for instance, we're also doing HY8.
Okay, I was kind of curious.
Mm-hmm. Yep. And on the schedule, you can see the corresponding textbook chapters, and that textbook chapter information can give you an idea of which terms you should learn. You know, rather than learning all those terms at one time in the semester, maybe it'd be best to start with like the chapter 16 terms when we're talking about that, and go roughly in the order that we're learning it. All right. Here's what it looks like when you just Google the phrase download HY8. The top hit is going to be a link to the Federal Highways Administration, and just right there, HY8 version 7.60, and you just click download. It's archived, it's a zip file, but once you decompress it, the installation is in there, and it's fast, it's easy. Okay, weirs. In hydraulics, weirs are used to measure flow. And one of the things that we can do to measure flow in an open channel is just put an obstruction. Like if it's a concrete channel, the water's flowing downstream in a manufactured, engineered concrete channel, if we put a big step in the middle of that channel and it's big enough, what it will force to happen is critical flow over that step, where the surface of the water will actually dip down and flow at this special depth. And if we know it's doing that, we can quantify the flow rate with the weir. So that's the summary, or the real quick introduction to what a weir is doing, is you'd use it to measure how much water is going through the channel. And so the disadvantage of a broad-crested weir like this is that this step tends to accumulate trash. Debris like sediment or logs or whatever gets in the creek is going to accumulate behind this weir. And the other thing is that you lose some energy. Like it can obstruct the flow, and the water depth can get deeper upstream because you've put in this step that the water has to flow over. Well, it can cause choking upstream. And so there's some disadvantages with a broad-crested weir. This is a side view of it. Instead of using a weir, there's another way to quantify flumes that eliminates some of those disadvantages. And a flume, rather than having the channel contract from the bottom up, like the step that the water has to flow over, in a flume what we're doing is we're making a channel temporarily narrower. And so by forcing the water to flow through a narrow channel, we're doing the same kind of thing, where what we're going to do is create a relationship between depth and flow rate. You know, we can have an equation with a weir that says, I just showed you that equation here, Q as a function of H. And so H is the depth from the energy grade line down to the height of the weir. So we wanted to know flow rate, and what we can actually measure is Q. So we can do it with the weir, or we can do it with the flume, and flumes are better because there's not sediment deposition and it doesn't cause energy loss or choking upstream. And so the reason why it avoids sediment deposition is, this is kind of now an angled view. I've got a side view in just a minute, but the advantage is that actually the water speeds up as it goes through the flume, and so it scours any sediment that would have settled. Instead of slowing down like it does upstream of a broad-crested weir, a flume accelerates the flow, and so there isn't going to be settling of the sediment. What we do, you'll notice here where it says gauge, you measure the water depth before the water goes through a contracting section and then down a slope. You can't quite see the elevations. Let me move on to this view. This is from the top, and what it shows is that the channel is getting narrower, and we're measuring the water depth before it gets to a throat. And the throat is where there's a really steep downhill section, and we also measure the depth in the throat for a reason I'll explain in just a minute. But let me go back now to the side view of this flume. So we have, you can kind of tell here in the approach, and then in the throat it's going downstream, and here's the side view that shows it a little bit better. So we're measuring the depth before the water goes down, and in the downhill section in the throat we're also measuring the depth there. Now we're doing the same kind of thing where we're using this to predict what is the flow rate. Think about a farmer, and the farmer is drawing water from an irrigation canal and sending that water out into fields. The farmer, maybe if you're in the western United States, there's limits on how much water can be extracted. They have what are called water rights, and so a farmer is allowed to use a certain amount of water each day, and there isn't an instrument like an electronic gadget that says how much you're taking out of the creek. I mean, if there's a pump, of course, you can quantify the flow rate that way. But in open channel flow, it's a little bit more tricky to know what's the flow rate. And so what this Parshall flume would allow the farmer to do is, you'd set up, it can be even plastic, or they may have a concrete flume that they send the water through before it goes into their fields. They would measure the depth of flow, H sub A, that's the height of the water at location A, and then you'd plug it into these empirical equations that manufacturers of flumes have come up with. There are these standard designs that have been out there for a long time, and they've calibrated to know for a certain depth of flow what is going to be the flow rate Q going through a flume. Now the tricky thing about the flume is that if there's a lot of water downstream, so let's say that you've put the flume into a creek that's pretty shallow, and so the tailwater is just talking about where the water goes after it comes out of the flume. If the tailwater has a pretty high depth, then the hydraulic jump that forms inside of the flume is going to be submerged. And so these equations that are right here are called free flow equations. They assume that this hydraulic jump that's occurring isn't choked by the tailwater. But sometimes if the capacity of the channel downstream is kind of poor and the water level is high downstream, then that can cause the hydraulic jump that's occurring inside of this throat to be drowned. And so you just have to apply a correction, is all it is. You're measuring the depth in two locations, and if B is really high compared to A, that tells you I'm going to still use this equation, but then I'm going to apply a correction factor, because B being so high reduced the capacity through the flume. So what we're going to do to get a feel for that is we are going to work through a problem. We're not going to do it today though, because I don't want us to rush through it and make it an afterthought, but let me just walk you through the process so that we can jump right into the example problem when we get together on Wednesday. You're looking at the ratio of B, the downstream depth in the throat, to the depth A, which is the depth in the converging section. So we kind of want to look like what's the ratio of depth. And this is a limit. If you are above this limit, then that tells you you have to apply a correction factor. So if B is, for instance, in a 30 centimeter width throat, if the depth downstream is 70% as high as the depth upstream, then beyond that you'd have to apply a correction factor. Below that, you don't have to apply the correction factor. You can just use the free flow equation that we had to begin with, this original equation. But if B is higher than the criteria limit, then you have to correct. And the way that you correct is with a figure like this. Now this is a figure that's specifically put together for a throat width of 30 centimeters. And there's curves like this for a whole variety of other throat widths. You know, anybody who designs or manufactures culverts, and like who would do that? Well, there are concrete manufacturers that have precast culverts, and they have all of the engineering design drawings and all the hydraulic calculations already prepared for their culverts. There are people who make them out of fiberglass. Like if you want a portable one and it needs to be strong but also light, fiberglass is a material that's pretty often used. But you know, like if you went to a farm supply store out in the western United States, they'd probably have a section where they're selling these Parshall flumes. By the way, Parshall was the name of a guy. It's not Parshall spelled incorrectly. That was a person. So what you do is if the downstream depth in the throat is too high, then you'd correct. And you'd look up like what is your specific B to A ratio. And so you'd find like what percent submergence is there, and then you'd find out what is the upper head. So if you had measured an upper head of 0.3 meters and it was 80% submerged, then you'd go down and find what is your correction volume. You know, like how much of the flow rate do you need to subtract off of what the equation itself gives you. So that's what we're going to work through. We're going to go through that process in class, and I'll also explain this correction factor in addition to the correction amount. I don't want to get into that now, but we're going to work through this example first thing on Wednesday. So what should you do? Let's just go to these announcements. The homework isn't going to make a lot of sense yet, but it will as of Wednesday. So I think really what you need to focus on is if you don't already have the textbook, I'd encourage you to get that. The textbook is mentioned on the syllabus. We're using Water Resources Engineering by Mays. Some of the homework assignments will come from the book. Some of them will be from me. But you'll need the book to help you like put together a big stack of flashcards. How long has it been since you made flashcards? Probably a long time, right? Make some maybe recently. Well, make some flashcards with these definitions. It would be a good idea. Fun date, cheap date, right? Hey, let's go over my hydrology flashcards. Jeffrey.
I was just looking at your card class. It says second edition, but when I was looking at MU bookstore, it says you only offer third edition.
Oh, okay.
Is that adequate? Because I have that book too.
Third edition's great. Second or third. The main thing that you'll want is access to like the concepts and terms. And between the second and third edition, they're not going to change what a nomograph is. Some of the homework problems may have changed. I need to double check and see if I have the third edition. But if you want to buy the second because it's cheaper, then that'll be fine.
Also, it also said you need to pick up a digital code for the online textbook as well.
Who said that?
On the bookstore, when I looked up.
Did you buy the digital code?
Yeah.
Okay.
Yeah. Well, I was looking at what books I needed.
How much was it?
For a new online digital code, like $148.
Okay. Let's make sure you get your money's worth. But if you want to buy or rent the second edition, it'd probably be pretty cheap. Anybody get the second edition? Whatever you get's fine. But get something. Are there any other questions? All right. Well, let's wrap up a whopping 2 minutes early, and I will see you in class on Wednesday.